Recording. All right. I'd like to welcome everyone to Codex. Our speaker today, we're very happy to have Professor Vern Paulsen. Professor Paulsen is a professor of pure mathematics at the University of Waterloo. Over the past 40 years, Professor Paulsen has made substantial contributions to a variety of research disciplines, including operator theory, frame theory, and quantum information theory. His seminal work on optimal frames for erasures has since spurred an entire research community to study optimal codes in projective spaces. He's also made noteworthy strides towards the eventual solution of the Cadison-Singer problem, and he is the namesake of the well-known Paulsen problem in frame theory. Since joining the faculty at Waterloo, his research has been strongly motivated by topics in quantum information theory, and his talk today is no exception. So I'd like to welcome Dr. Paulsen.
Well, thank you very much for that kind introduction. I'd like to talk about a new and different approach to Zauners Conjecture that maybe isn't very well known yet, that uses the theory of entanglement breaking maps and sort of comes out of a quantum information theory perspective. So this is based on, let me see if I can get this. Okay, this is based on a paper called Entanglement Breaking Rank and the existence of SIC POVMs. I know most of you know that this is an equivalent restatement of Zauners Conjecture in terms of quantum information theory. Since we published this in a math physics journal, we use the word SIC POVMs instead of Zauners Conjecture, but I'm going to stress the Zauner Conjecture for this talk. It was joint work with two of my thesis students, Satish Pandey, who's now at the Technion, and Jitendra Prakash, who's now in Copenhagen, and postdoc, Mizanur Rahman, who's now at the, in Goa, India. Let's see, okay. So what I'd like to do is give an analytic perturbative approach to Zauners Conjecture that's rather than algebraic. I think that's the main new thing that comes out of this perspective. And the other new thing is we're going to be looking at completely positive maps, which are often called quantum channels in the literature, as a means to get at Zauners Conjecture. So here's the version of Zauners Conjecture I'm going to be looking at. It says that for each dimension d, there's a set of d squared unit vectors, which are equiangular. So the inner products of any two distinct vectors is the same value, and that value is necessarily 1 over d plus 1. So most approaches that try to solve this problem, they want to express these vectors exactly, and to do that you have to use exact arithmetic. So you can't just do it over the real numbers, you have to look at some field extension of Q, and then it becomes more of a problem in algebraic geometry. So my emphasis is I'd like to try to turn this back into a problem in analysis, and that's hopefully what we'll be able to do. So I'm going to be using completely positive maps. So I know that's not familiar terrain for everyone. So I wanted to start with just a brief overview of CP maps. So I'll always use n by n, mn to denote the n by n matrices. And when I write mn of md, I'm thinking of block matrices. So this means each entry is a d by d matrix, and then you have n squared blocks. So of course, it's just, if you forget the extra parentheses, then you just have an nd by nd matrix. Or those of you who like tensor product notation, this is also can be thought of as mn tensor md, where the d by d matrix that's in the ijth block represents the matrix unit eij in mn tensored with that block matrix. I always use a superscript plus for the positive semidefinite matrices. And then something that plays a role in quantum information is when you have things viewed as tensor products like this, you'd like to look at the positive matrices of a special form, the ones you can write as a P in the first space, tensored with a Q in the other space, and then take their convex combinations. So that's a strict subset of the ND by ND positive matrices. It turns out it's a difficult subset to describe. Deciding if a matrix is in this subset or not is an NP hard problem. Then we call a linear map between two matrix spaces positive if it sends positive semidefinite matrices to positive semidefinite matrices. And then there are these, what we call ampliation maps, which is, if you think of it as a tensor product, it's just the identity on the n by n tensored with phi. But I really like to think of things in terms of block matrices. So you just form block matrices over MD. And if you apply phi to each entry of a block matrix, then that gives you a block matrix over MR. And that's what this map phi upper n is. And then the map is called completely positive if not just phi is positive, but phi upper n is positive for all n. So the most famous example is if you look at the transpose map. The transpose of a positive matrix is positive, but if you did transpose upper n, what you'd be doing is you'd be taking a big matrix and you wouldn't be fully doing the transpose, you'd just be doing a transpose in each little block. And that's, when you do that, that doesn't preserve positivity. So this is sort of the canonical example of a map, linear map that's positive, but not completely positive. Maps which are completely positive and preserve trace. So the trace of the image is the same as the trace of phi of x is the same as the trace of x. Those are called CP-TP maps. And in quantum information theory, that's what's called quantum channels, because these are the mathematical models for what can happen to quantum states under various kinds of quantum effects, quantum operations. So, so generally, these are what are studied and used as the models for what can happen in quantum information theory. So the Choi's theorem gives us a very easy way to understand completely positive maps. And it says the following. So again, I'll let these EIJs be the standard matrix unit basis for the D by D matrices. And Choi showed that a map is completely positive if and only if when you form this block matrix by looking at the image of the matrix units under phi and put them together in a block matrix, that's a positive dr by dr matrix. And that matrix is called the Choi matrix, or sometimes the Choi-Jamliakowska matrix, but I can never spell Jamliakowska. The third thing he proved is that the third equivalence is it's if and only if the map has this special way of being written. It's pretty easy to see if you have something written in this form and you put a positive matrix in, the output will be positive. And it also works when you ampliate. So every map of this form is completely positive. And Choi proved the converse, that if it's completely positive, then it has such a nice representation. These are called Choi-Krauss representations, and math physicist Krauss had actually studied this earlier than Choi. And the other nice thing about this Choi matrix, besides being an easy test to tell if a map is CP, if you ask for what's the smallest number k so that you can write a map in this form, that's what we call the Choi rank of phi. So this form isn't canonical. There can be many, many different ways to express phi as such a sum. But the Choi rank is the minimum number of matrices you need to do this. And it turns out that that's actually equal to the rank of the Choi matrix. So you have a very easy way to tell if you've got the minimal such representation of a map. So that pretty well tells us what completely positive maps are. Entanglement breaking maps are a special subset of the completely positives. So a map is called entanglement breaking if you start with a positive block matrix and you apply phi to each one of the blocks. If it's completely positive, we know this will be a positive matrix. But entanglement breaking, if it's more than positive, if it belongs to these separable. So the reason for this language is any positive map that's not in the separable, any positive matrix that's not in the separable matrix is what's called an entangled positive matrix. So entanglement breaking just takes arbitrary matrices, which may be entangled or not, and disentangles them. So hence the term entanglement breaking. These were appeared quite a few places in the literature, but the first people who studied them seriously were Horodecki, Ruskay, and Shor. This is the same Shor as Shor's algorithm. And they came up with a lovely characterization of entanglement breakings. So the first condition is if you look at the Choi matrix, it's not just positive semidefinite, but it itself is a separable matrix. And so remember, this is an NP hard problem. So that means it's NP hard to decide if a map is entanglement breaking or not. The third characterization is it has a Choi-Krauss representation where all the matrices that appear are rank 1. And then the fourth and fifth are if anytime you take a positive matrix and do the composition, you get CP, or anytime you precompose with a positive, you get CP. So they are sort of the things that you can hit with a positive and they stay CP. So even though this map psi is not CP, your composition will be CP. So it's kind of interesting if you could come up with any ways to decide 3, 4, or 5 that were easy, then you'd be proving, say, that, well, if you could find a polynomial algorithm for 3, 4, or 5, then you'd be proving P equals NP. So that means 3, 4, and 5 should be equally hard to decide. So because this every entanglement breaking map has this special form, we decided that it would be interesting to study what's the fewest number of rank 1s you need in such a thing. And that's what we called the entanglement breaking rank of a map. And so our paper really started off as just a study of how does this entanglement breaking map behave, what can we say about it. But as soon as we started to look at examples, we found some surprising things. So let's look at a few examples of maps. So the first map, first off, I'll just look at maps from where the domain and the range are the same size to keep life easier. If you look at the identity map, the map that just leaves X alone, well, one way you could write that is identity times X times identity. So that shows that it's CP, it has the Choi form. It also shows that the Choi rank is 1. So if you wrote down the Choi matrix of the identity map, it has to be a rank 1 matrix. But on the other hand, if you do transpose, which is positive composed with phi, you just get the transpose back. And transpose, we said earlier, is not completely positive. So that means this map is not entanglement breaking. So the interesting thing that tells you is if you try to, it tells you there's no way you could write this formula, phi of X equals X, is a sum of rank 1s ever, because then it would have to be entanglement breaking. The next map is a map that it's called the completely depolarizing channel in math physics. It's just a map that takes every matrix to a scalar multiple of the identity, and the multiple is just the linear functional trace of X. So if I did trace of X over D here, this would be a CP-TP map, and that would be the quantum channel called the completely depolarizing channel. This one, it's pretty easy to see that it is entanglement breaking by just writing out a sum of rank ones. If you use the matrix units, then you can see that this map is just given by pre and post multiplying by those. So the way to sort of see this is if you do Eij x Eij star, that's Eji. And when you do Eij x Eji, that just picks off the Jj entry of x. And then the output is the matrix unit EII. So as you sum over all j, you get the trace of j times EII. And then as you sum over all I, you get the identity matrix. So here's a way to express this using d squared rank 1 operators. On the other hand, the Choi rank is d squared. And the Choi rank is always going to be smaller than the entanglement breaking map rank, because that's just the smallest number you can use in any sum. And so this, but this calculation shows the entanglement breaking rank is bounded above by d squared. So we get that the d squared is the Choi rank, and that's the entanglement breaking rank for this map. So that's one map where we can write down what this number is exactly. So the next interesting family to look at is suppose you take this nice entanglement breaking map and you perturb it by multiples of the identity. You know the identity is not entanglement breaking. What happens? Well, you discover that it stays entanglement breaking for all t's in this interval. And so if you try a larger t, it'll be completely positive. If you go for a t past 1, it'll be completely positive, but no longer entanglement breaking. Also, you can compute the Choi rank of all these, and everything in this interval, the Choi rank is d squared. So that's a lower bound on this entanglement breaking rank. So we set ourselves the problem of just saying, well, what is the entanglement breaking rank as a function of t for these maps? And you'll see in a minute why we still don't know the answer to that. So we wanted to know what it is for t's non-zero. So the other thing that's interesting is, right, this t equal 1, that's one of the endpoints. That's the cutoff point where you stop being entanglement breaking. Let me give you a little bit better feel for what entanglement breaking means. If you think of writing a rank 1, as I like to think of vectors always as column vectors. So this is the column times the row. And if you write out what happens when you do that, you get yk star xyk. Well, that's just the inner product of the matrix with the vector. So that's just a scalar, and that number can pull outside, and then you're left with an xx star. And so when you write it as rank 1s, it's exactly the same as writing it as a sum of functionals times rank 1 positives. And these functionals aren't just any functional, but they're vector state functionals. So another way to think about the entanglement breaking rank is it's the smallest k so that you can express your linear map in terms of vector functionals times rank 1 positives. Okay, well, here's our theorem. So the first thing we discovered when we tried to work out what the entanglement breaking rank of the endpoint was that Zauners conjecture. So this is kind of a surprising way to look at Zauners conjecture. So you can express that map phi1 using d squared arbitrary rank 1 operators, if and only if Zauner is true in dimension d. So what's going on here? Well, if you can write it as d squared, then you can prove right away that all of the rank 1s have to be rank 1 positives And then you show that the d squared vectors that correspond to these rank 1 positives are your equiangular. The other thing we could say is that only happens at the endpoints. If you're strictly inside the interval and you write it as a sum of rank 1s, no matter how many rank 1s you need, then they can't be positive on the inside. Notice I don't have the other endpoint, and we don't know much about what happens at this other endpoint. I'll come back to that later. And then the thing that gives us something perturbative is that you can show that if you could prove that the entanglement breaking rank of these phi t's for t less than 1, if you could show that there were enough of them so that their lim was less than d squared, and that's enough to show that Zauners conjecture is true. So that gives us this sort of perturbative. By studying these maps where we don't have rank 1 positive, we have sort of 2 sets of vectors, that's somehow studying that for t close to 1 gives us perturbative ways to try to understand Zauners. So the proof of none of this stuff is hard. I'm not going to do it here because it's just messy calculation. It uses all kinds of clever things like, well, you assume that you have phi of 1 written as a summation of rkx, rk stars. And you do things like you plug the identity in, and that tells you something about the vectors. You use the fact that you can say exactly what the map phi of 1 composed with phi of 1 is, and just do a few things like that. You evaluate it at the matrix units, and you eventually grub around, and you get this result that the RKs have to be positive semi-definite. What allows the perturbative result is it's very easy to show that this function, entanglement breaking rank, is something that's lower semi-continuous. So the value at an endpoint always has to be smaller than the limit as you approach the endpoint. So if the limit as you approach the endpoint is less than d squared, then the value at phi of 1 would be less than d squared, and hence would be d squared. So this proof suggests that if you don't want to have to think about all this stuff with completely positive maps and all, it's somehow telling us that when we look at this map phi sub t and take its Choi matrix, that those are some nice family of positive maps that as t goes to 1 gives us something that is exactly Zauners conjecture. But looking at ways to decompose those Choi matrices for t near to 1 should be something that's perturbative approach to Zauner. So you can sort of forget all the CP map stuff if you like, and just think about these Choi matrices. And it's just I don't think we ever would have thought of looking at those particular Choi matrices if not for this entanglement breaking rank business. So here's what we think is true. We think that not only is the entanglement breaking rank at t equals 0 d squared, but that it's d squared throughout the interval. So that means for t not 1, we would need to find 2 d squared vectors, right? To make up these rank 1s, we'd need xk's and yk's. They're not positive when t is away from 1. So they've got to be a set of 2 vectors. And then somehow this is like an unfolding of Zauners conjecture, because as you take t closer to 1, the x's and the y's have to be converging to the same vectors. And so it's that converging that really led us to our second conjecture. And that is, we think that if you can find these vectors, these 2 d squared vectors for each t, that you should be able to actually solve continuously. So that means there should be 2D squared continuous vector valued functions from the unit interval into C of D, which at time 1 are the same vector, but are distinct for all other times. And then if you look at those rank 1s that they induce and sum up, that should give you this map phi sub t of x. And so we've done the brutal verification by hand of this in the dimensions 2 and 3. We can write down the nice continuous vector valued functions that do this. So we're nowhere near Zauner yet. We've got 2 and 3 dimensions. We know our conjectures 1 and 2 are true. And this summer, we're trying to write down what the functions are in dimension 4. What I really think is going on is that not only are these vector valued functions continuous, but they're smooth. And so our approach is to write down the differential operator for what these have to satisfy. You differentiate everything with respect to t here, and you get some like Lie bracket equations that you'd like to solve that differential operator. Now at t equals 0, we know we have a solution because at t equals 0, there are 2D squared vectors that do it. And we'd just like to prove that that differential equation is solvable at least in a neighborhood of t equals 0. So that's what we're up to right now. So we don't know if these conjectures are equivalent to Zauner or if they're stronger. It could be that 1 and 2 are just actually equivalent to Zauner's conjecture, and there's some way to see that equivalence without actually proving whether Zauner is true or false. But we haven't seen any way you can go from what happens at t equal 1 and pull it back to smaller values of t. So yeah, as I said a minute ago, I believe there should at least be an interval near 0 where conjecture 2 is true, because I think we should be able to prove these differential equations have local solutions. They're highly nonlinear equations though, and many, many variables, right? Because it's matrix valued, so it's quite a few entries. The other thing that's baffling to us is we don't, if you remember, we didn't have things for the other endpoint, this t equal -1 over d. So that's also an entanglement breaking map, and we don't really understand it very well. It could be that Zauner is equivalent to it being d squared also, that somehow it's just some neat transformation of Zauner's conjecture that we're just not seeing. Or maybe it's a totally different problem in geometry, having this be d squared. So we don't even know for the moment if they have to be positive matrices or if it's giving us, 2d squared sets of vectors if it was d squared. So that's a bit of a mystery we haven't unraveled yet either. The other thing you can do now that you have this viewpoint of Zauner is you could try to make partial progress on Zauner by finding upper bounds on this entanglement breaking rank. So, maybe we can't prove Zauner, but maybe we can at least get that we're close to Zauner with some bounds. So we thought a little bit about that, and this is what we have there. So we know that this phi1 is entanglement breaking, so it can be expressed some way as a sum, or we couldn't have shown it was entanglement breaking. But the way we show it's entanglement breaking uses d to the 4th terms in the sum. On the other hand, we know somehow that it always feels like Zauner is somehow related to mutually unbiased bases. So what is going on there? Well, if you do have D+1 mutually unbiased bases in CD, then they allow you to prove that the following upper bound on the entanglement breaking rank. So this gives kind of a nice new perspective maybe on the relationship between existence of MUBs in Zauners. MUBs is upper bounding the entanglement breaking rank of this map phi sub 1. So the CP maps approach, I think, allows one to find related equivalent problems to Zauner. The thing that has me excited about it is it seems to quickly give new things which are equivalent to Zauner that I find difficult to see from a frame theory perspective. Many of you will recognize the things on the next slide as things you know that are related to Zauner, but it's kind of sweet the way it pops out of the CP maps approach. So the only thing I'll really use here is this little lemma that if you have a map phi, and you look at the map you get by composing phi with the transpose on the left, or the map on the right, then what you can show is that phi is entanglement breaking if and only if psi is entanglement breaking. And not only that, but the entanglement breaking maps, the entanglement breaking rank of the two maps is exactly the same. So this means if we start with our phi sub t's and we compose with transpose, then we get this one parameter family of maps, which is trace of X, identity, nothing happens to that when you compose with the transpose, plus, well, I've used T twice here, sorry. This is the parameter T, and this is X transpose. So if we look at this family of maps, these will be entanglement breaking because phi sub t's are entanglement breaking, and their ranks will be the same. So we could try to study entanglement breaking rank for this family of maps instead. And here's what that leads us to. So Zauners conjecture will be true in dimension D if and only if the entanglement breaking rank of this one is D squared. And now when you look at the Choi matrix for this one, you discover this is what it's telling you. In this case, the D squared rank 1 operators that you'd use to represent psi 1 they're not positive, but they're the form x, y star, where the y's aren't x star, but they're x bar star. So you first do a complex conjugate and then take. Moreover, if you had these, then the representing psi sub 1, then when you look at the vectors xk tensor xk, this is the thing I'm sure most of you who are familiar with Zauner are familiar with, is this connection between Zauner and projection onto the symmetric subspace of this. So that the vectors that work to give you psi 1 would be a Parseval frame. Well, there's some constants here, which I'm going to ignore, but a normalized type frame for the symmetric subspace of CD tensor CD. Remember, the symmetric subspace is the, you look at the flip operator where you send a vector x tensor y to y tensor x, and it's the subspace fixed under the flip operator. And so because we get this sort of automatic that if we take any rank 1s, they have to be of this special form, then it also tells us that Zauner is true if and only if you can write the projection onto the symmetric subspace as rank 1 operators of the form xk tensor yk without specifying what the yks or xks are, just if you have any decomposition that gives you into these special rank 1s. And then also we get the same perturbative result, that if you look at the limit as t goes to 1 and of the entanglement breaking of rank of the psi t's, and if it's smaller than d squared, then Zauner's conjecture is true. So you can study Zauner's conjecture by looking at these psi t's and trying to find their entanglement breaking rank. So what is causing the symmetric subspace to show up here is when you look at this psi of 1 and you form its Troy matrix, then basically you get projection onto the symmetric subspace. This is this block matrix inside MD, tensor MD, and it's really up to some constant is the projection onto the symmetric subspace. For the phi of t's, we know that the Troy rank of phi of t is exactly d squared. And so when we're trying to prove that the entanglement breaking rank is d squared, we don't have a lot of room to work. Right? Both writing it as a general sum and writing it as a sum with rank 1s would have to be exactly the same. So for that reason, these psi's have a slight advantage in that their Troy rank is strictly smaller than d squared. So maybe you've got a little more wiggle room. You know you can, for sure that you can write them as this many non-rank 1s. And because you need fewer than d squared non-rank 1s, maybe that makes it easier to work with. But so far we haven't found any advantages, but it's just this gut feeling that maybe it's a better thing. It also gave sort of a nice example where you can say that you have an entanglement breaking rank whose Troy rank is strictly smaller than its entanglement breaking rank. Those aren't so easy to come by. And didn't really see any in the quantum information literature. And so just let me sort of end by stating the analogs of conjectures 1 and 2 in terms of the psi t's. So conjecture 1 is equivalent to saying that the psi t's have rank, entanglement breaking rank d squared in the whole interval. And conjecture 2 is equivalent to saying that we've got these continuous vector valued functions that give us psi of t. Well, I left out the gory details because I wanted to give you the overview picture rather than the grubby stuff. So I'm done quickly.
All right.
Thank you for your attention.
Yeah, thanks so much. There's a little button at the bottom of your screen labeled reactions where you can react. And we will end the recording.